I'm not compromising on time. 17. OK, thank you very much. Well, again, thanks to our organizers. We start on mathematics now, so if you are tired and you thought it's going to be easy, buckle up. But we'll try to be gentle nonetheless. So I'm going to talk about the prediction of the density of states. Some of this has appeared already in Marcel's talk, but I'll try to give you another point of view on this maybe. First of all, a reminder, most of you know the story, but since some of the people in the audience actually knew, we are talking of the Schrödinger equation, and this thing doesn't work, but fine. So we are talking of the Schrödinger equation, linear Schrödinger. By potential, I mean V. This is one particle equation. It's linear, no problems there. The landscape is the solution to Laplace u plus Vu equals 1. Again, honest to goodness 1, actual 1, number 1. The difference between the two, as you are well aware of, is there is an infinite number of solutions to those. Typically, you care maybe not about infinity, but many. There is one solution to the landscape, which is unique. So the entire game is to show you that you can squeeze out an immense amount of information from this one solution, which applies to this infinity of solutions. I'm going to talk in principle about the eigenvalues and density of states as opposed to eigenfunctions. So our favorite toy is the integrated density of states, which means that I'm talking about the number of lambda i's below a certain level lambda. So I always mean the integrated one. And we are going to try to do it using the landscape. So first of all, you saw in Marcel's talk this beautiful separation into the subregions of the landscape and how the eigenfunctions appear, at least what he called the tribe of fundamentals, one by one, in the shells, wells defined by the landscape. The question which you might or might not have posed to yourself is, thank you so much, in which order it happens. So for example, you have such a potential. This is randomly 0 or 1 on a grid. This is your V. The question is whether looking at this, you can tell me where is the first eigenfunction, where is the second, where is the third one, and so on, and which shape they have. With the shape, you kind of saw it already that the landscape predicts it, but where is the first, the second, the third? Well, turns out that this count by the minima, which Marcel has showed, actually trivially tells you that, where the first deepest minimum of 1 over u is of the effective potential. This is that u, 1 over that. You have the first eigenfunction. The second one corresponds to the second, third corresponds to the third, and so forth, together with the shapes. So these are the 4. How do I make a light out of this? Come on, you are all LED people and none of this is working? Yes. Thank you. That's the collaboration. So 4 deepest wells of 1 over u, 1, 2, 3, 4 together with the shapes. First 4 eigenfunctions, 1, 2, 3, 4 together with the shapes. We are speaking fast, so I'm not sure you're absorbing this. Think about it. You have one solution to Laplace u plus v equals 1. One solution, not infinite number of. I'm squeezing out a lot of information from this. The eigenvalues, in principle, this would be sort of 4 solutions for equations. All of these are predicted by the landscape. You would tell me 4 is not so impressive. Well, it turns out that there is a much deeper correspondence than that. It turns out that the eigenvalues are actually proportional to minima of 1 over u, at least for what Marcel has called the band of fundamentals, the tribe of fundamentals. Sorry. With the constant, which is a simply dimensional constant. It does not depend on the potential. It does not depend on the disorder. It does not depend on your indium composition or whatever you want. It's a dimensional constant. It's 1 plus dimension over 4. The error is about 2% in the particular computations that I showed you, and the location of the minima corresponds to the location of the sort of accumulation of the maxima of the eigenvalues with an even better error. Now, this is so far an observation numerics. Again, I have showed you this with 4 eigenvalues. I'm sure you are not impressed. This is 100 eigenvalues. So you have a 2D potential 80 by 80 grid. First 100 eigenvalues in blue, first 100 minima. This is this curve divided by this curve. You have 1.5. almost on the point. I promise you that this does not depend on the potential. I'm taking a very different potential. This is correlated. This is something common from the cold atoms, actually. Very different curve of minima, very different curve of eigenvalues. The ratio is, again, 1.5 on the point. Now, there are obvious problems with this assumption that you can do things by minima of 1 over u, which some of you have already raised, and they are pretty clear. It's pretty clearly talking about the fundamentals to you. What are the obvious enemies? If I have, let's say, one well, I'm promising you that this is working forever. So in particular, in periodic structures and one-well structures and so on. Let's say 1 over u like this. There is only one minimum, so you'll predict the first eigenvalue. Well, you would like them all, right? You don't want just the first one. Another example, you are taking so this is your 1 over u. You are taking 1 over u, which is just tiny bit, fluctuating. Do this minima count or do this minima not count? Will you have an eigenvalue here, eigenfunction here, and eigenfunctions there, or not? Or how are you counting here? Is it 3 of them or 1 of them? Or luckily, in the semiconductor structures that have been presented here today, it doesn't matter so much, but as a mathematician, I can give you obvious counterexamples. It's obviously, it cannot possibly be correct. But nonetheless, even if it's correct, it's for the fundamentals. Next case. Much bigger estimates that Doug will be showing. This is the actual density of states, not integrated density of states. This is histogram of 1 over u, very close. Now, let's get away from the fundamentals. You would say, well, maybe you can only predict the tribe of fundamentals with this. Well, let's take another look. You have what we call the Y law. N, again, is the integrated density of states. This is what you would get with the Y law associated to the original potential V in green. In blue is the reality. In green is the original potential V, or what Y law would give. In red is the one with 1 over u. The Y law is asymptotic. It's a theorem. It's true. But it's asymptotic over here, meaning that you have a correspondence of all 3 over here. The Y law with 1 over u appears to work from day one. Another potential, Bernoulli, meaning 0 or 1, the Y law with V would give you the green curve. The reality is blue curve. The Y law with the landscape gives you the red curve. Another example, periodic potential. Again, more or less exactly on the point. We have discussed this issue. The band gap is not really captured, but everything else is. OK. Now the theorem. And I promise you it matters. So the problem that we had through it all, yes, I have my 3 minutes. The problem that we had through it all is that there was not even a conjecture corresponding to this. We could not, we could obviously derive mathematical counterexamples to every statement we were making. I'm saying there is a theorem behind it. And while there are constants, you as physicists can take constant 1 or whatever corresponds to it. And the theorem says that you have to count minima in the cubes of side lengths lambda to minus 1/2. So in order to approximate the integrated density of states, what you are actually doing is you are taking your big system. You want the integrated density of states at the value lambda. You are chopping it into cubes of size lambda to minus 1/2. You are looking for those cubes on which minima are below lambda. So these are cubes where minimum of 1 over u is below lambda. And you are counting the number of these cubes. This will alleviate both problems here. Well, it's also a theorem, so it is true. But this will alleviate both problems here. I mean, as you go up, you will be counting correctly. As you go up here, you will be counting correctly too. You will have all and the trick is that this will give you both the approximation by the minima and the approximation by the integrated density of states. And this, in a sense, explains, if you think about this, why the landscape works so beautifully. It's because it gives you the exact correct length scale. And that's why 1 is not 5 and not 55, and that's important. Because this length scale, the fact that you observe your eigenvalues at the scale lambda to minus 1/2, that's where you expect them to be, is the same as the length scale given by the landscape. And that's why you can prove that the landscape gives you the same slope of Urbach tail and things like this, or Lifshitz tails, as you say in mathematics, and so on and so forth. I'm 1 minute.
All right. Okay, thank you, everyone. In the interest of time, I will move on. We're talking about localization of eigenfunctions and the effective potential we've all met many times. So I'm going to start with the simplest possible example, which is almost the same as the example that Marcel discussed, but not quite, because we're going to consider an unbounded domain. We're going to consider all of the real line and a square well. All right? So this is a square well which has bottom 0 and has top.
David, is there a blue or a black pen?
It's too faded. This is my time. Oh, there's pink. Phenomenal. Yeah, great. Well, here's the blue. So anyway, this is a square well. Its bottom is 0. Its top is what I'm calling V bar, which is the maximum of the potential. It's just constant. And this is a totally elementary calculation that the eigenfunctions, which have been drawn many times, maybe here's an orange in here, are, well, there's a fundamental here. It's not actually supported here, right? It's got an exponential tail outside. And then there's the next one, which, well, sorry, it's supposed to go up and down once. Whoops, sorry. Well, anyway, whatever. Okay, so this well fills up with a number of eigenfunctions, but the tail is exponential, and the rate of decay, that's beautiful.
I hope it works.
Yeah, the rate of decay is given by the coefficient. That's just a trivial ODE, right? I mean, the solutions are exponential, but of course, because it's a bound state, it has to decay, so it only has the exponential factor that decays. So this is a trivial fact which was known to, Euler or something like that. And Agman observed that it's true in n dimensions. It's true in all dimensions and for very large families of potentials. And so what he introduced was the analog of the exponential function, which has the right length scale. And well, so this was on one of Marcel's slides as well. And so is it the green dot that I'm supposed to be doing here to get this? Does this work? Is it this one that works? All right. So if you integrate this distance here, this is the arc length, you will get exactly the distance in the 1D case, except that the potential is allowed to vary. And this is just exactly how much it is happening. And so this was well known to Sturm and many years ago. And so what Agman did is he formulated this theorem a little bit more precisely. He said that if you take this natural distance associated with the potential, it's sort of how much the quantum particle difficulty the quantum particle faces, and then you take the distance to the well, so just how far away you are based on how much headwind you have, or if you like, the walls of the jail to the trapped particle, the jailbird, which is in here. It can, some of it, or with some probability, it can escape out to here, and maybe to get a little farther, it takes it much more work. So anyway, that's this Agman distance. It's just the geodesic distance weighted by this quantity here. And what Agman proved is that, in fact, in a very, very large family of cases in all of Euclidean space, you have this exponential decay exactly on the nose, well within epsilon. And maybe the constant depends on epsilon. It depends on a little bit on the threshold. You can't be up to the energy level. You have to be just a little bit below the energy level for this to work. All right, so this is a relatively simple theorem, and it's fundamental, and it was used mostly for the ground state for many, many years, and it's an elementary fact. And it's very, very closely, so that the mathematical techniques associated with it have to do with just multiplying by exponential weights of various kinds for special functions which are well suited to the differential equation, and using the right truncation. So it's some kind of scaling having to do with the natural distance associated to the operator. So this is what Agman did. So what we did was to introduce this new effective potential. We conjugated the equation. You've seen this already. And this is also extremely old idea. The first person who used it in my knowledge is Jacobi. And he used it to show that, to understand the property of the shortest distance between points on things like the sphere. He was able to discover that Legendre was wrong and didn't understand the second derivative test in the calculus of variations, and that the correct test involves a quadratic, the appropriate notion of second derivatives involves a quadratic form, just as it does in the minimum of any multivariable function. And he did that actually by dividing by something. All right, so, but then through history, there have been, dozens of places, especially in elliptic theory, where people have divided by some suitable solution and compared it to some other solution. And so this is the appropriate thing to do. At the stage when I got involved in this subject, we knew, obviously, that this special function was a superposition, right, of these states, right? It was this. And so if you know already that the eigenfunctions are localized, obviously U reflects that. And Marcel made the point that U should be big where psi is big if psi is a spike. That's perfectly natural. But the other things that they had discovered were much, much more detailed than that. You have to understand that this series is very slowly converging. There has to be a phenomenal amount of cancellation in order for this to possibly have anything to do with anything. So it was quite mysterious from the rigorous mathematical point of view, whether there could possibly be any rigorous reason why this was true. And the fact that the function decays according to the potential 1 over u, that 1 over u is the wind that it's fighting, was important. Anyway, what happens is simply that because of the equation and because of the clever gradient estimates of Agman and other manipulations which we had to do, we were able to show the analogous decay properties associated to the effective potential. So we just changed the definition of the Agman distance, and fortunately, you've already seen this once. All you do is you plug in where you see the potential, you put in 1 over u. That's the only change. So that's it. It's the same notion, and we've seen it before. And then there's an actual theorem. So I'm actually going to state a theorem here, like Svetlana. This is the exponential decay. Now, it isn't quite the same exponential decay that Agman proved. The theorem is different and the methods are slightly different. The exponential decay is on the level of square integral. It's sort of the energy density of the particle, which is decaying. You can't get the L infinity decay by a mile. Furthermore, so the beautiful thing is that the constants are totally explicit and understandable. And this is a universal theorem in the sense that it's not even just true for all of these systems that we've been describing, but also probably for graphs and definitely for manifolds and things which are much, much more general geometrically than purely 1, 2, and 3-dimensional things. And it's completely independent of the size of the region. It's independent of t, no mention. This is an absolute constant here. These are physical quantities, the maximum of the potential versus some spectral parameter, which is the distance between eigenvalues. And all of the rest of it is matched to be scale invariant. And it doesn't have to be a periodic lattice. It can be anything. So it's, as I say, it's a practically universal statement. And the corollary is relatively tame it says that if you can check something about 1 over u, so it's a conditional theorem. It says that if you can check something about 1 over u, then you'll know something about the eigenfunctions and the eigenvalues, that they are definitely going to be localized. Now, I want to describe to you, so I'm going to show you, am I done? Okay, what we've gained. Well, what we've gained is that the Agman gave no information for the potential, and now we have some information, at least on the bottom of the spectrum. And in these examples, such as the Bernoulli potential, you have this unbelievable match, which is that if you take such a Bernoulli potential, which you saw before, the Agman distance matches all the way along. This is 14 orders of magnitude, whereas the potential as it was originally written down, the capital V is useless. It is the distances. Here you're getting one of these is the ground state, and the other one is the Agman distance, and they match. So anyway, the theorem justifies this to some extent. I do have more to say, but I'm going to let you, we haven't proved everything. And I will have to explain that in the unsolved problems section.
So next.
He emailed me that one just today.
But I don't think that's necessarily bad. We'll go over them again. So I'm going to sort of do the same thing, except as a computational mathematician, I have a tendency to think about the landscape function. Well, is this a numerical algorithm? Does it tell us how to compute the eigenvalues and the eigenfunctions of a disordered Schrodinger operator? So let's do this as a test. And this is a torture test here because we have the world experts sitting here. And my PI colleagues are not allowed to play along because they've seen this before. But I'm going to play this as a game, a sort of Where's Waldo, but it's Where's Ground State. This is the potential, a 1D potential on a domain that goes from 0 to 256. There's 256 unit length pieces, which are assigned a random number from 0 to 4. I take h bar squared over 2m to be equal to 1, and we solve Schrodinger. So are the eigenfunctions, say the ground state, going to be localized? We would expect so because it's highly disordered potential. And then the question is, where does it localize? So it's not a statistical question, not what are the statistics of the localization, but actually for this realization, where should we look for the fundamental eigenvalue? Anyone have a guess? Should it be the deepest well, the fattest well, the well with the highest walls? What's that? What is that? Deepest and the fat. Well, okay, so which one do you pick? Since volunteer from the audience. So let's use the landscape function, if nobody's willing to guess. So we compute the landscape function, solve one Poisson equation, trivial, and I've left the potential behind there, and you can see it's, of course, it brings the peaks down, it brings the wells up, it smooths things out, and now you clearly have a deepest well, and a second deepest well, and so forth. So this gives us a prediction. This is the fundamental state, this is the second, this is the third, this is the fourth, and so on. They should occur there. The next thing I do, I don't use Marcel's watershed basins. Instead, I take a sub-level set. I go up a multiple of this eigenvalue, and I look at everything below the effective potential. That gives me a width for each eigenfunction. So this is my prediction of the eigenfunctions. Obviously, I didn't get their shape, but I have a prediction of their location and their width. And then we can, of course, in this simple 1D example, I can compute the exact eigenfunctions and see how I did. And here's the match. So you see they occurred exactly in the right order, in exactly the places we expected, and you get a real sense of the shape. So that's where Waldo is. So now you know the rules. Let's play the game again. This potential. He says it's the same, but he wasn't looking at the axis. There's much higher amplitude. Otherwise, it's the same.
This is Alkian, not anything.
So we compute the landscape function, and the landscape or the effective potential looks totally different. It much closer matches the real potential because of this high amplitude. It has a much different opinion of where the deepest well is. Actually, the deepest well is the deepest well now, 1, 2, 3, 4. They're not quite in the same order as for the potential. And the sub-level sets are much thinner, so my prediction is that. And then you compare it to the true eigenvalues, and it's a perfect match. And I think Svetlana or somebody showed, well, this was the Bernoulli potential that percolates. You do the same thing. You compute the effective potential. You look for the wells there, the 4 deepest local minimum, 1, 2, 3, 4, and the sub-level sets associated with them, which leads us to that prediction. Here's the true eigenvalues superimposed, and now I put them together, and you see you get a lot of information. So the only thing we haven't gotten here is the real shape of the eigenfunction. I'll get to that a little bit later. I'm going to skip this because Marcel went over this in great detail about how using 1 plus d over 4 times the depth of local minimum gives you a very good idea of the eigenvalues. And also I'll skip this because Svetlana talked a lot about Weil's law is another way, you've seen these pictures before, how well the effective potential give you a lot of eigenvalues. Let me talk a little bit more about, and yeah, so this was more of the Weil law. Let me talk, oh, and this one too. Everything I've done people have stolen before me, but what can I do? So this is the situation of computing. This is the density of states, not the integrated density of states. So this is a histogram of the eigenvalues from the lowest one over here up to all the eigenvalues less than 1, computed. This was another one of those 1D potentials, only this one had 500,000 pieces with amplitude going from 0 to 4. And there it has 7,000 eigenvalues less than 1, and here's the histogram. That takes 40 CPU hours to compute, even for a 1D problem, because I'm trying to compute so many eigenvalues. I think I'm not going to take questions. I don't have a lot of time.
I'm sharing. You can have a question.
Okay. What is the functional shape of this state?
Well, that's an interesting question to try to pick this up, but
Yes.
You have the data in front of you. That's a history. I can mail you all 7,122 eigenvalues out to 6 decimal places. I didn't fit it in. I mean, we can do a fitting, but we'll just get some numbers.
Behind Doug's back before it was erased. E to minus c lambda to minus d over 2, and c is exactly the probability that you have a potential under.
I know, but you have not spotted it.
It's exact. It's exact.
I know that it's exact, but I'm asking you about the functional form.
Well, again,
So this is one realization, and we would have to take a lot of statistical data.
Minus c, e to power minus d over 2.
So the point of
It's pure exponential in the bottom. It's an Urbach tail. It's pure exponential in the bottom.
So what we could do if we were trying to estimate this is do this for a lot of different realizations and then do get a fitting to a smooth curve. We couldn't easily do it when it takes 40 CPU hours to produce one of these, and especially if we were in 2D or 3D where it would be impractical. So we do it again with the landscape function, and instead of computing all the eigenvalues, I compute all the local minimum of the landscape function less than 1, and that takes 5 CPU minutes, and it gets this picture, and you can compare the two. It seems very likely that you would get the same information, but I haven't pursued it beyond that at this point. And then finally, let me use my last 3 minutes to talk a little about the Agron distance. So I'm going to present it again, because if you didn't see it, it went by a little fast with David. The idea is the following. You're walking over some landscape, and we're going to put a cost functional. The higher the landscape is, the more it costs you to walk. We'll consider it like walking twice as far if it's twice as high. Specifically, we weight the landscape by how much the effective potential is greater than some energy value that we set up. So to compute this Agron distance, you have to give a potential function. We'll use the effective potential. And you have to give an energy value. And you see how much W exceeds E. The plus means if that goes negative, you just set it equals 0, the square root. And we use that to weight the distance between any 2 points. So if you take any path, then you multiply by that factor or integrate that factor over the path. And then you take the shortest path, and that's the Agron distance between the 2 points for that W and that E. Okay, and then using the theorem that David quoted, the eigenfunction decays exponentially in the Agron distance if that point is the peak of the eigenfunction. So we can estimate all those things using the effective potential. We use W for the function in the Agron distance. We use the peak that we estimate by taking a local minimum of W to give Y, and the energy level we use are 1 plus d over 4 times the height of the minimum. And that's how we got the picture. You didn't see this picture, I don't think. The top picture is I just graphed that. So I take the effective potential, I compute these quantities here, and I graph that. So now I don't just get a width and a point, I get a shape. I get a predicted eigenfunction, and it has a lot of structure. And then I compute the exact ground state for this problem, and you get this one. If you look at first glance, you say they look pretty good match. Pretty good match, and the eyeball norm is often off by 10 or 15%. You can see this one's a little bit fat. It has some of this structure at the bottom, but not quite the same structure. So then I thought a little bit, could we do anything to improve that? But before I did that, let me go to this picture. You saw this one in David's talk. This is the log of the last picture. It's the last picture on a logarithmic scale. And the point he was making, again, they're pretty good in the eyeball norm, but they're not exactly the same. But the point is you go over here, and it says where the contour line of 15 orders of magnitude less than the peak is, and it's in basically the same place as the contour line on the true one. Not exactly the same shape and not a perfect match, but you get the magnitudes way out using this. How can we improve it? Well, suppose you're trying to solve some nonlinear system. Everybody knows how you do that. You use Newton's method. If you have a good initial guess, that'll converge like a bat out of hell. Getting the good initial guess is hard. I got a good initial guess. The same thing for eigenvalues is called the Rayleigh quotient iteration. There's a bunch of iterations for eigenvalues. If you have a good guess of an eigenfunction and a good guess of its eigenvalue, then you can use the eigenvalue guess to improve the eigenfunction, then use the new eigenfunction to improve the eigenvalue. That converges very quickly if you have a good guess. And here's the one. This is my good guess that I got from the Agron distance. This is one Rayleigh quotient iteration, which costs like solving one more Poisson equation. This is the second, this is the third. These three all look exactly the same. In the eyeball, you can't tell the difference, and they all look like the true eigenfunction. Thank you.
Okay, our next speaker from the University of Orsay. He was the chairman of the Department of Mathematics at Orsay, which is a big mathematics department in France. And as you know, mathematics in France is big.
But I'm almost relieved of all those functions now, so yeah, I'm feeling better. Okay, so I understood the game in a slightly different ways than my colleagues, which means I was told to say who I am and what I'm doing here. I'll mostly say who I am and not so much what I'm doing here. But at the same time, I hope it's going to be pleasant recreation because you're tired. Okay. So who I am, Claude says. What sort of things I'm interested, when I'm not doing localization. I'm essentially interested in studying the nice properties of sets, and I like a certain number of types of sets. So I mentioned 3 here. One was the sort of sets that you get when you try to do image processing using something called the Manfrottin functional, which I decided not to talk so much about. Okay, but you would try to find a simple picture that looks like a given initial picture. That's one of the games. Game number 2, free boundary problems. So you have, I don't know, something like 2 fluids. They have some interface. You don't know where the interface is, but you try to guess how nice it's going to be, okay? Hoping to prove that it's sufficiently nice that the problem makes sense, okay? And then there was this third mention of harmonic measure, which is you send a random particle in the air. You have a surface. You look at the first time the particle hits the surface, and you ask questions about, how often do I hit a given region compared to some other regions? Are there places which are hidden from this arrival of the random particle, and some regions that are always going to be obtained? And how does it depend on the regularity of the boundary that you're given? Okay, just the same sort of things. All right, and I'm of course interested in theoretical results about this. So this is just the only thing that I will say about image segmentation, right? So you take this beautiful image provided by Antoine of a kagoo. So I don't know how you say kagoo in, yeah. And essentially the thing that we mathematicians can produce is this, right? And okay, and again you try to minimize some functional, and the game I would be playing is to prove that to some extent the boundaries that the functional decides for you is reasonably smooth instead of being horrible or looking like a counter set or whatnot. Okay, and I decided to talk a little bit about soap films again. I mean, because because the notations will not be too horrible. Okay. So what's a soap film for you? Well, you know. What's a soap film for me? Or you know, what is the Plateau problem that mathematicians like to solve? Let me make it simple. You take a curve in free space, and you try to look at a surface which is bounded by the curve and which has as little area as possible. And when you do this, you say you solved the Plateau problem. And in particular, one of the things that you have to prove is that given a curve, you can find a surface that minimizes area. And for you guys, it's normal. For us, it's a complicated problem, okay? Which was solved many times. And I explained a little bit about the many times. What happens is that there are, in fact, various ways of trying to say what is meant by minimizing surface. Okay, and here I'm only talking about, I'm going only to talk about some notion which is Hausdorff measure. In our case, it would be of dimension 2, which is exactly the same thing as surface measure when the surface is smooth. And otherwise, it has the advantage of being defined on sets by a simple formula. But I don't give it to you. Okay, so that's one thing that I decided to do, but many other people prefer to use slightly different notions. And then there is also a discussion about what do you mean by being attached to a curve. And that's not as obvious as it looks. So for instance, you would have this obvious thing that says that, you know, it has to contain the set, because that's one way of being attached. But that's this one is not functional. Okay? And the way I like to think about attached to the set is that the thing is attached to the set in the sense that if I try to move the set any way I like, in a continuous way, but the points that are on the boundary have to stay on the boundary. Okay, I'm not allowed to pull it off the boundary. Then this is one of the possible moves, and then I would minimize surface measure on all the possible moves. That's my definition. Okay, it's amusing because it's also the definition for which there is no existence theorem known at this time. Okay, and again, so the thing that I would like to do for my life would be, for instance, try to prove existence for this problem that I mentioned to you, which surprisingly is not known. Okay, and then in order to minimize notation, because I was told that notation, even the good, beautiful notations from mathematicians were not always easy to understand by physicists, I'll try to minimize notation by showing pictures. This is one surface. It's, okay, so it's maybe not completely clear here. There is something that looks vaguely like a disk, which is tilted. And then there is, it's a communication between something that looks like a disk and something that looks like a plane. Okay.
Is that an experiment or is that a math?
So this is a computation experiment.
But that's a soap film?
But I can easily do soap films that look like that. But the pictures will be less beautiful. Yeah. Okay. And again, there is some strange thing which is that I have an idea of what is a soap film, and it's some object that minimizes area. You guys have an idea which is something, and something which is extremely surprising to me is that the two things coincide within very small errors, to the point that you can ask whether this is a simulation or you know, real picture, right?
What's in between? What is that?
So the disk, so, okay, so, and the reason why, let's say, how many minutes?
4.
Wow. Okay, and I thought I would be finishing in 2 minutes. Okay. When you have two planes that meet like this, SOAP doesn't like it because it thinks that pinching this way or pinching this way, this is SOAP of dimension 1, and it's not good. What is better is something like this because it takes less surface. And this is exactly what's happening here. Okay?
That's exactly the grain boundary problem.
Okay, good. See? So some communication. This is the same picture when you put your finger here and you didn't wet your finger before. You have something, and this is also my way to answer the question about should you take as a definition the SOAP film contains the boundary. And here the SOAP film does not contain the boundary, and it's a perfectly agreeable thing. So what I'm interested in is taking SOAP films, proving that they are smooth or having a local description of those guys, and then eventually maybe this could be used to prove existence. Okay? Existence is hard to prove in particular because you don't know what the set is going to look like when it tends to being minimum. Okay? This is the theorem of Jean-Taylor, 78, I think, or something like this. And Jean-Taylor says every minimal set or almost minimal set, like a SOAP film or a SOAP film, has exactly this structure, a smooth part, a place where free surfaces can meet with 120-degree angles. That's singularity number 1. Singularity number 3 is at this point you can have 6 surfaces that meet with equal angle and make it full. And you can try all these SOAP film experiments that you want to do in your life. In principle, you're never going to get something more complicated than that. Okay? And I'm trying to prove so this is another example of Jean-Taylor's theorem. This I think is a theorem which says that the only way you can meet a surface at the boundary, which is what I'm interested in, is like this. Okay, so this is the only singular point that singular type that can happen when a SOAP film meets a surface. Okay, and my question here is what happens, for instance, when this thickness tends to 0? What happens to this set? And here, unfortunately, I don't have a complete description to give to you. This is a conjecture. The previous one was a the boundary that I'm interested in is the great diagonal. The thing is looking like a cube. This is the cone over the set of cube. We believe, I think, that this is a true minimal set, which means that, for instance, when the density will tend to 0, thing will look like this. Okay, but we don't have a proof that it's minimal. What do we expect? Okay.
It has been done?
You mean proving? No. And again, it's one of the, near the boundary, there is something, I'm saying experiences are very good. In fact, not when you're getting close to the, capillarity plays a role. So for big pictures, it's very easy for me to say this is SOAP film, they look alike a lot. For knowing whether precisely this thing is here, even if I try to make very thin wires, capillarity will create some sort of a horrible mess and I want to be able to see. So I can't, okay, right. This is one of the behaviors that I know I can prove exists, okay? V-shaped thing that goes off and on the thing. And then I didn't even put the picture of a one which I expect to be true, that would complete the story, but I cannot prove that it happens. Okay, thanks. Sorry.
Okay, now that was the...
Yeah.
We did, right,
There's a
okay.
timer there.
And I can use this, okay. Okay, I've been working on mostly organic molecules which behave as semiconductors. It's pretty obvious that organics are rarely crystalline, and particularly when they're polymers, they're very disordered. That they work as semiconductors where it's possible to move charges around useful distances is probably a great surprise. So to have some new toolkit to try to understand what localization or possibly delocalization means in these systems is very exciting. So we've been pleased to be brought into this consortium, and we're working out how we fit in. How do I make that? Does this work? Okay, I'll use this. It's fine. It's okay, I'll use this. So what I wanted to do is to give you a sort of very simple background to the sorts of materials we work with and where we hope we can find some points of contact. And the most attractive point of contact is to see where we can mirror what has been done with the gallium indium nitride systems. So here is a little primer on organic materials. They're very often colourful. The colour is associated with pi electrons. That's electrons associated with the second of the double bond for carbon-carbon linkages. So this chain here, which is a string of benzene rings with vinylene groups between them, is a polymer we found very useful some time ago because we managed to make a light-emitting diode out of it. It's quite colourful. It's a sort of yellow-green, very fluorescent material in solution. And it derives its colour and its semiconducting properties for exactly the same reason as graphene does. So here is a honeycomb network of carbons, which is graphene, where the conductive properties, or the semiconductive properties, come from the electrons associated with the carbon-carbon double bonds, which delocalize pretty much in the same way as the valence and conduction electrons do in gallium nitride or silicon. So this polymer chain, as you can see, we can sort of fit it onto the honeycomb network, which is a quick way of explaining that the electronic structure is essentially the same, but whereas graphene has zero band gap, most of our organics, when they are more confined and smaller, we can bring the band gap up to be useful values across the visible spectrum. So the question that has complicated the field, because it's quite hard to address, is what sort of electron states do we have? If we manage to go two-dimensional and get a graphene sheet, we know that we can take a standard textbook on silicon and to describe the correct quantum states for the valence and conduction electrons as delocalized states where momentum is a good quantum number. But actually, when you start to look at many of the physical properties, there's pretty clear evidence that wave functions are pretty localized. So if you look at these the colourful properties of these materials, the long polymer chain, which in principle has delocalization of electron states of the length of the chain, is not very different to quite short molecules. So there are many reasons why that localization comes in quite strongly. And actually the localization tends to be good for getting light emission. These are very fluorescent materials. It's that fluorescence that is harnessed these days, and the use of organics as the light emitters in OLEDs, organic light-emitting diodes, is used in expensive smartphones and expensive TVs. They have been managed to be engineered to form, certainly in display applications, pretty good technology. Now, as it happens in those applications, they're very, very thin, stacked organic layers with a whole stack of heterojunctions, as we heard earlier today, is done in the nitrides. And we're not too worried about disorder because we can put quite large electric fields on and pull carriers through fast enough to make the diodes work. But a more testing device is a transistor, and there is a sort of a few decades worth of effort, a lot of it relatively empirical, working through different molecular semiconductor materials, trying to pull up the mobility of charge carriers. So the horizontal green line labeled ASI as amorphous silicon. Amorphous silicon is a sort of benchmark because that's what's used to make transistors that switch the pixels in crystal displays. And what you can see as a function of time, which shouldn't necessarily correlate with the physical property, mobilities have now done quite well. The mobility is up at, in the commonly used old-fashioned units of centimeters squared per volt second, up at 10 or more. And what that means is that carriers must travel as waves, must have mean-free paths that are quite considerable, maybe up to tens of intermolecular spacings. So though there is disorder, it is not catastrophic. It is definitely possible to support wave-like and relatively delocalized motion. Why that is a puzzle. If we want to, one of the measures of disorder that we've now come to look at quite seriously is measuring how sharp the optical transition is at the bandgap. So measuring the Urbach energy, which we heard a lot earlier today, is now done fairly systematically. So this is a plot of absorption coefficient versus photon energy. The logarithmic slope is a measure of just how disorder is broadening out the absorption edge. And this is a plot of some relatively well-ordered organics, which do give these mobilities that require that there is some level of wave-like propagation.
1 over the slope is Urbach energy, right?
Yeah, that's right. Yeah. So the Urbach energies of a bit more than KT at room temperature. Well, actually, there's 24 MeV is the best number, which is not as good as. Well, the nitrides are probably not that different, are they?
No,
About the same.
15,
Yeah.
20, but I don't know if small is good or not.
Well, for the organics, 24 is a really good number, and in the past the numbers were much worse. But they've been brought. There are some materials where the numbers are, if you like, in the same ballpark as the nitrides. So it could be that we go looking for understanding extraordinarily low mobilities, and the mobilities in some of the LED structures are down at levels of 10 to the minus 6, I mean, really low numbers. We're perhaps more interested in understanding how we can get the mobility up. So one of the models, and this is a slide that my colleague Henning Seringhaus in Cambridge put together, of a sort of a starting point, is looking at relatively crystalline materials. So these are molecular crystals of materials like pentacene. That's the example shown here. And Simone Frattini is going to talk, I'm sure, much more about this tomorrow, where a sort of frozen phonon displacement of the molecular positions within a crystal lattice actually define quite a well-defined, a well-structured sort of disorder. It turns out that the overlap of the pi electron wave functions from one molecule to another are extremely sensitive to orientation and separation, and that the disorder produced by just vibrational motion is almost certainly the disorder that controls transport. It's not exactly the same as the alloying that is done with indium gallium nitride, but it is a realistic starting model that we want to explore to see whether that can be matched onto localization landscape. This is a slide with lots of stuff that I'm not going to explain because I shall run out of time. But one of the other interests about exploring how we can get relative delocalization is that many of the properties of photosynthesis, and in parallel what happens when we make solar cells with organics, seem to require that carriers or excitons can travel very quickly at large enough distances to, for example, avoid electrons and holes staying within one another's Coulomb capture cross-section. And we have evidence where we have ultra-fast optical measurements in Cambridge where we can track how quickly electrons and holes move apart. The velocities that they move apart at very early times, down at sub-picoseconds, are up at band velocities. And we think that that is absolutely critical to the operation of, well, solar cells and probably photosynthesis. So again, understanding delocalization is interesting there. So for some reason, a picture has disappeared. This is there should be a structure of a lead halide perovskite. The second category of disordered materials which we are working with, it was on my laptop but it's not here, are the lead halide perovskites, which there would be a little picture of a cube with a structure with chemical, the repeat unit is ABX3, where A is methylammonium, B is lead, and the X3 is triiodide. You may have heard of perovskites, lead halide perovskites, as cheap and cheerful solar cells. This is a field that sort of came out from nowhere in about 2012. Have I run out of time? Yes. Where, in spite of huge amounts of disorder, it is possible to make solar cells that apparently have very, very clean band gaps and have solar conversion efficiencies as good as silicon. They are materials where, again, the Urbach energies are in the same ballpark as the nitrides. They shouldn't be, because they are full of far larger amounts of disorder than they should have if they're going to work well. So that's another set of materials where we want to see whether we can use the localization landscape formalism. I'm looking at Claude. I should stop. I've got some more slides. Okay. You can make LEDs out of them as well.
Is that your?
That's mine.
book?
Okay.
And just use the down arrow.
Yeah, I'll just use the down arrow.
And I'll set a timer over here.
Okay, great. So I'm just going to tell you a couple things about what we're doing. A lot of the work related to the Simons project was actually covered in many of the previous talks, especially the work with UREN. And these are some of the previous people who have worked on it. And I'm forgetting one person of the current group, which is Mortiza Monavarian, who just joined my group as a senior scientist in the group. And then these, of course, are the main collaborators I've worked with, and also with Suji Nakamura very closely and Steve Denbars on the materials growth in MLCVD. So if you go out and look at the posters, okay, a lot of our work actually started with atom probe tomography. And Bastian Bonoff is a senior postdoc in my group who's a world expert in atom probe tomography, and he's really at the cutting edge of trying to do absolute quantification of atom probe tomography and nitrides. 30 seconds on atom probe tomography, very sharp tip made to a radius at the tip. This is usually a model of a cone with a sphere on top. The tip radius is on the order of 50 to 100 nanometers, depending on how it's prepared and the tool that's actually been used. It's cooled to cryogenic temperatures on the order of 10 to 50 Kelvin, but typically 20 Kelvin. A very large electric field is applied to it. And then there's a very slight heating, either through a voltage pulse, okay, or light, okay? And that causes a very small, short thermal spike. And then atoms leave the tip, and then it's time-of-flight mass spectroscopy, okay, to a position-sensitive detector, okay? So the clock gives us the mass-to-charge ratio, okay? And if it goes well, okay, we'll count atoms, okay? And depending on the optics, the ion optics in the tool, typically we'll either capture 1/3 of the atoms or 2/3 of the atoms with no Z sensitivity. So that's the technique. So we get atomic resolution, chemical maps of the material without any Z sensitivity. And that's how it works. When we had this tool, Yuren Wu contacted me and said, I'd like to come do a sabbatical at UCSB, and that was approximately 2012, right? 11. The papers came out in 12. Okay. And he said, I have 2D and 3D near atomic scale Schrödinger-Poisson drift diffusion solvers. And I thought, this is fantastic, because we have three-dimensional atom maps, so we can actually start putting this together. That was the big excitement in starting the collaboration. And what we found very early on in the collaboration with Yuren was that if we look at transport and LEDs, as we heard many times today, the solvers that we actually use, which are 1D, which are the standard outstanding solvers, like from Sergei Karpov's company, typically overpredict one of the very important physical properties, which is actually the voltage that we apply to the device, okay? And voltage is everything for us when we talk about efficiency, because voltage corresponds directly to what we call the electrical efficiency of the device. We would like our LEDs to be operating at a voltage very close in EV, which we call that the applied bias in EV, so the photon voltage is equal to the applied bias or less actually on the diode. That's something that we work very high on. If we have excess voltage, we have inefficiency. So it turns out to be a huge issue in our work on efficiency. And this is what a typical LED looks like. When I answered Richard's question about do we do this empirically or scientifically, we were trying to use landscape theory to have a rational design of diodes, okay? And the world is being illuminated by solid-state lighting. It's one of the very few things in energy usage that has led to a marked transition and reduced electric usage, okay? It's actually in the United States, for the first time ever, there's actually been a downturn in total electricity usage in this country, and it's almost 100% due to solid-state lighting. And so efficiency is everything that we work on. If you look at Bastian's poster, this is basically from atom probe tomography with this near atomic resolution maps. This is the input that we actually put into the landscape theory simulation. So we go from real experimental data that we get. This is actually what we feed into the landscape simulation. So this has been very exciting. Most of these layers, we understand what they're doing, but the real action in the LED, this is the N side of the junction that you heard about in the Claude's talks and the subsequent talks. This is this P side of the diode. This is a layer that blocks electrons from going too far, also during Sergei's talk. Most of the action is right here in this top quantum well. The role of these lower quantum wells is controversial. The role in this pre-well structure, superlattice, is controversial. This is probably for making the material more pure. We're actually not sure what all these quantum wells, but if you add them, the devices get brighter. That's the empirical optimization. We would like to understand that better. Okay, so in atom probe tomography, I already gave you the highlights. The resolution of the technique is materials dependent. In the axial direction, it's near atomic. In the radial direction, it's several atoms. That's an estimate, okay? So I want to give you just, I'm going to skip a few slides because of the time. I want to give you a story on our current work and our previous work. And so this previous work is that when Yuren did these beautiful calculations, I thought we needed a simpler test structure for studying the transport. So everything you heard about today in the devices, what we call bipolar devices. We inject holes, which is the absence of an electron in a normally occupied state, and electrons in excited states, and hopefully they recombine if we're trying to make light. Okay? This is a bipolar device, so we have electron and hole transport. The problem is that much of the modeling is extremely dependent on the recombination coefficients. Okay? So I said this makes simpler structures, which are LED analogs, for unipolar transport. And so this is where we've done a lot of work in unipolar transport. And so David Brown in his thesis did a lot of work in unipolar transport, as did Mika Fireman. The future work from Clayton Kwa, who's here today, Mortiza, okay, and Bastian, is actually to make p-type structures so that in unipolar vertical transport we can actually understand hole transport. And I didn't make a slide on this, but what is enabling for this is bottom N to P tunnel junctions. That's essential for these experiments. So we need a bottom N to P tunnel junction for current spreading. And so if we're unable to make that, then they have a different project, basically, because it's essential for our work. But I want to give you the impact of this, okay? Our president talks about a wall. You heard about it? Okay. So this is what the wall looks like. This is not the band profile. This is gallium nitride. This is aluminum, gallium nitride. This is gallium nitride. This is APT data from by Sheki Mazumdar. I think this is pre-Bastian APT data. Okay, and so this is an alloy of a larger, much larger band gap material. Aluminum nitride has a 6 eV band gap. Gallium nitride has a 3.4 eV band gap. This material here, very simple, doped with electrons right up to the wall, and electrons on the other side. This barrier height, okay, is on the order of several eV. And no electron, when we vertically bias the structure and forward or reverse bias, should get through this, okay? Because this barrier height is on the order of 10 kT or larger. Nothing should get through. And if you did this in the second or third gradiest semiconductor system ever, gas, nothing would go through. It would be a perfect barrier. And this is way too thick, the way that we've grown this, okay, to have any tunneling. Okay, this is way too thick to have any tunneling. So what do you think the IV is going to look like when Mika or David applies a bias between this two-terminal device? This is like, where's Waldo? Do you think you'll see current flowing? Or is it just going to be a barrier? How much bias do I have to apply to this to get current to flow? This is about the way we've grown this is about a 2 to 3 EV barrier. So 3 EV? Yes. Okay. It's ohmic. And we did this experiment over and over. We took dislocations out of the structure. Okay, and this is the whole basis of Mika-Feierman experiment. The natural alloy fluctuations in this system, what should be in classical 1D simulations, okay, I think using your software, okay, this may be Bandinge, this may be your software, okay, is that you see this is 5 EV, these barriers are about 2.5 EV large. There are percolative transport pathways through this, okay, that are due to the alloy fluctuations. This was a huge takeaway message. In LEDs, the big issue is that we cannot drive holes deep in the structure. We can get electrons all the way to the top quantum well. We cannot drive holes deep in the structure. So again, this is the work from Martiza and Clayton, is to understand the real barriers for hole transport experimentally. There's no rectification there. This looks like a short, okay? So in vertical transport, and this is really what motivated much of my interest in all this, in the nitride alloy systems, and these are the 3 important alloy systems. Indium gallium nitride is the recombination medium in light-emitting diodes. Algan is the standard barrier material. And there's another very exciting, more extreme alloy barrier material, which is indium aluminum nitride. It's harder to grow, but it's very attractive for many physical reasons. So we have both large bandgap changes, and due to the polarization discontinuities, which are a sum of differences in spontaneous polarization between the barrier or the surrounding materials, okay, which would, often it's gallium nitride, and the alloys, okay, from strain and spontaneous polarization, strain-induced polarization, okay, provide huge barriers for carrier transport, even when the band gap is smaller. So the classical 1D simulations fail. We have percolative transport on the nitrides for an additional reason here that I also have to include, is that we have large band gaps. So we have large band gap fluctuations. We have strain fluctuations, and the effect of the strain fluctuations is that they give polarization fluctuations. Polarization fluctuations gives fluctuations in space charge. Space charge means that due to the spatially varying electric field combined with the band gap changing, there are low energy pathways through these alloys. It's a remarkable result. You would never see this in the AlGas gas system, which is the mother system for semiconductor alloys and heterostructures. So I'm over time, and the other thing that I just wanted to add, because there should have been one more point here, is the other reason in nitrides that we see these strong effects is that the effective masses are actually quite large. Large effective mass means that the carriers are very localized in space. The effective masses in the nitrides are very high compared to the mother system, which is gas, AlGas. Okay? So that's the 4th reason that we see these effects. So I'll stop there. So before everybody goes, so Cheyenne, Martiza,